Welcome to Advanced Programming with Java at Portland State University. In this screencast, we'll learn about developing small device applications with Android. The Android platform is designed to work within the constraints of small devices. The Android platform includes a stable and secure operating system in which you can run powerful applications even on small devices. Applications may be developed in several languages, but Android is best supported using the Java language. So in this screencast, we'll cover several things. We'll talk a lot about the fundamentals of Android. We'll also look at some of the APIs for developing Android applications. And finally, we'll talk about some of the tools and techniques for testing Android applications. Now, before we dive into this lecture, I want to talk about the structure of the content that you're about to see. This set of slides is all about the fundamentals of the Android platform. We're going to be seeing a lot of slides, a lot of words. Yes, we'll be looking at APIs, but there's some things that we aren't going to see. In order to understand the entire Android development platform, I think it's important that we know what command line tools are out there, the kinds of things they use, how Android applications are put together, even though a lot of that might be hidden by other tools. The build system, Android Studio, things like that. We'll talk a lot about the Android APIs, APIs for working with the Android system itself, and then also APIs for developing applications inside Android. We'll learn a lot about the Android APIs and how they can be used. However, there will be subsequent screencasts that really demonstrate how the tools are used and how Android applications are developed. Okay, so what is Android exactly? Android is an application development platform that has several parts. Now, like any software system, it ultimately needs to run on some hardware. And for Android, it's a small device. The Android platform is designed to be device and vendor agnostic. However, it does provide for means of leveraging device-specific hardware for increased performance. There's also the Android operating system. So this is an operating system that's based on Linux. It's a real operating system and can do a lot of the same kinds of things that Linux can, and does what any good operating system should be able to do. Provide access to device resources like the GPS system, the camera, telephony, the network, and Bluetooth. Running on that operating system is the Android runtime, or ART. Android applications execute inside the ART, and it's the ART that translates the application's bytecode instructions into the device's native instructions. This translation happens when the application is installed on a device. If you're studying older resources about Android, you might see something called the Dalvik virtual machine. Well, ART is a replacement of Dalvik that makes a number of improvements in terms of performance and ease of use. Now, who are some of the people that are behind the Android platform? Well, there's an industry group called the Open Handset Alliance, which consists of a number of technology companies who want to provide an open platform for mobile device development. Primary output of the Open Handset Alliance is Android, which is a well-supported, free, and open device platform. The advantage the Open Handset Alliance provides all of these vendors is that it standardizes many aspects of the Android platform, which allows the individual vendors to focus on specialization, so have devices that work well for their market, while also working together to provide a better device experience overall. So what does it take to create an Android application? Well, there are several steps. First, you need to write the code. So this consists of source code of the application and also the visual layouts. Almost all Android applications have some image resources, icons, pictures, startup screens, things like that. Android development is supported on several languages, but the primary one, and probably the one that's best supported, is the Java 8 language. And one of the nicest things about Android development is that it's just like developing other applications. So it supports unit tests, richer UI automated tests, code coverage, all that good stuff that leverages professional software engineering techniques to help you go faster and safer. After you've authored the application, then you build the application and package it up for deployment. Android applications are built using Gradle, which is a successor to Maven. Once the application is built, then you can run, and of course debug, the application inside a device emulator. So these emulators are really great. What they allow you to do is explore how your application behaves on different kinds of devices. The emulators can also provide you feedback on how the application runs on that particular device. So you can look at how it uses system resources like memory and CPU. Finally, once you're ready to share your application with the world, you can publish your application to a marketplace such as Google Play. Next, let's look at some of the tools that are used to build an Android application. So the Android SDK, Software Development Kit, contains the tools and the libraries that you use to construct an Android application. The Android SDK is installed in a directory referred to by the Android Home Environment variable. What we'll talk about now is a series of command line tools that are used to build Android applications. It's these tools that are leveraged by Android Studio and Gradle to do like the heavy lifting of building and running Android applications. There are several fundamental tools that manage the Android SDK itself. Something called SDK Manager, which manages the package that comprise the Android SDK. Also another tool called AVD Manager that manages Android virtual devices. These AVDs describe the devices, the actual physical devices, that are simulated in the Android emulator. Not surprisingly, AVD files are kind of large, and they all reside in your .android AVD directory inside your home directory. There's another application in Tools bin called lint. It analyzes an application's code for quality problems in their structure. These are the kinds of things that could cause bugs, performance problems, instabilities, etc. They give you really good insight into the quality of your code. Like many linters, the Android lint utility detects problems, assigns a severity to each problem it detects, and you can configure lint to ignore or change the severity of issues of a particular type. In your source code, if you're doing something that you don't want the linter to complain about, you can annotate it with an @suppress_lint annotation to instruct the linter to ignore that issue. The tools that actually build an Android application are found in the build tools directory. Now, the build tools evolve over time, and so each version of the Android SDK has its own directory underneath build tools. Some of the build tools included in the latest versions of Android SDK are things like AAP2. This is the Android Asset Packaging tool, and what it does is it compiles the Android resources. So these are things in the res values files that we'll learn about later. It compiles all of these into a binary format that's ultimately bundled into a single Android package, or APK, that's nicely optimized for the Android platform. So again, this tool just deals with Android resources, things like images and bitmaps and some other kinds of things. It does not contain the compiled code, or the DEX bytecode, the Dalvik executable bytecode, that's compiled from your Java bytecode. There's also a tool called APK Signer, which digitally signs APK files. And so digital signatures allow you to verify the source, the author of a particular Android application. This, of course, is essential for the marketplaces. So in addition to managing the Android SDK and building application code in with the SDK, there's also a bunch of platform tools that manage the platform itself. A very important one is ADB, or the Android Debug Bridge. This is a tool that communicates with an Android device or an Android emulator and lets you do things like install and debug apps, does all the port forwarding for you, move files in between your local file system and the device, and lets you do things like taking a screen capture or a video of what's happening on your Android device, and also access the SQL database and profiler information. And again, ADB works not only with emulated devices, but also with physical devices. So if you've got an actual physical Android device connected to your local machine using USB, you can use ADB to access that, but you have to enable developer options on the device first. The Android platform provides a rather robust logging facility for your application and the Android platform itself to provide information about what's going on, log information. And those log files can be accessed using a tool called Logcat. Logcat allows you to filter and format log entries, and is also something that you can do inside the ADB shell. There are several tools that work with Android emulators, and those are all found in Android Home/Emulator. There's the emulator tool itself, which manages and launches the Android emulator. You need to provide a bunch of information to the emulator command, such as the device to be emulated, so which device from which manufacturer. That is the AVD, the Android Virtual Device. Emulator command also supports many options for the emulator, such as wipe data that will initialize the device's storage, just to start you over from the beginning. You can also configure aspects about how the emulator interacts with the outside world. So you can set properties of the network, such as how much network latency it should have, or what the speed of the network should be. And you can also configure attributes of the emulator environment, such as the time zone in which the device runs. Another tool related to Android emulators is the make SD card command. And this tool creates a disk image that emulates external storage for a device. So if you wanted to emulate something like an SD card, you'd use make SD card. So that's a brief tour through some of the tools that are used to build an Android application. Let's talk about Android applications themselves. So when it comes to interacting with an Android app, there are four primary mechanisms for doing so. Android apps have something called activities. And activities perform a single user-focused task. It's almost always through a visual user interface. So this is like, a page or a screen in your Android application. Every application has an activity called its entry point, and this is what's initially displayed when the application is started. Android applications may also be interacted with through their services. Services run in the background and provide things like data or behaviors to other applications. A service may run as part of an Android application or might run in its own process on the device. Components interact with services by binding to them, and then it's basically like a remote object. It can invoke one of its methods. Another mechanism for interacting with Android apps is something called a broadcast receiver. This is a facility that allows an application to receive events that are broadcast either by the operating system or by another application. So this is things for like alerts in your application. Android has specific support for that allows clear and consistent communication between the application and the lower level operating system. So while this isn't code, it's also important to understand the Android manifest mechanism for communicating and learning more about your application. So it's the manifest that provides the definition, configuration, and requirements for the application. This is used by the Android platform when an application is installed. This manifest is consulted to determine things like what permissions it needs and what system resources it needs access to. Protecting user information is a critical component of any software system, but it's especially important that applications that run on small devices provide their users with a lot of confidence that the applications that they interact with are secure and trustworthy. The Android platform consists of multiple layers of abstraction that provide different levels of trust and clear trust boundaries between the different layers. The first level of security isolation is provided by the Linux kernel itself. So this kernel provides user-based permissions, process isolation, and secure inter-process communication. The same things that you'd expect on any Linux system or really from any real operating system. One of the ways this is implemented is that each Android application runs as its own user in the system. So when an Android application is installed, a new user in the operating system is created, and each Android application also executes in its own process. This allows the kernel to enforce a sandbox and applies it to both native code as well as code that's run inside the ART. Now you might have heard of being able to root a device, and so what this means is that you can allow your application to run with the root user permissions. And this is sometimes necessary to debug an application, but in general it's not a safe thing because you're elevating the permissions of an application, and you're allowing it to do things that it normally wouldn't be allowed to do. There are also many Android devices that support file encryption, so this provides more kernel-level security that allows you to protect data if a device is stolen. Android has a very robust permissions model that empowers the user to decide if they'll allow an application to access information capabilities. So essentially, applications need user permissions before they're able to interact with things like the device's microphone, camera, its location, or the contacts. One of the things specified in an application's manifest is a list of the permissions that it requires in order to operate. The Android platform defines dozens of built-in permissions, but it's also possible for an application to define its own permission. This allows an application to interact with the services provided by another. When an application is first installed, the user is asked to grant the application the permissions that it needs. Now note that permission granting is an all or nothing operation. Either the user grants all the permissions to an application or none of the permissions. If at runtime an application attempts to perform an operation that it was not authorized to do, an error occurs. And a very important concept in Android application development is something called an intent. An intent is an object that's used by one component of an application, such as an activity or a service, to communicate with another. So for instance, when you want to start a new activity, something like compose an email, you use an intent. When you want to start or interact with a background service, use an intent there also. And also, message broadcasting is also accomplished via intents. An intent can either be explicit or implicit. An explicit intent will specify the exact application to which the intent should be delivered. And this is often used when you start an activity, a very specific activity that you want started, or starting a service in the same app. The other category of intent are called implicit intents. And what they do is they describe a general action that should be performed by any capable app. So for instance, let's say you have an application that has a URL link. If you don't want to browse to that URL, you issue an implicit intent to browse the URL. And this allows the Android operating system and potentially the user to choose which application it wants to respond to that intent. So you might have multiple web browsers installed on your Android device. An implicit intent will result in a little pop-up saying, hey, which browser do you want to open? We're going to start a deeper dive into the Android Programming API. We're going to start with a class called Context. Context is in the Android.content package. And this represents the application in which components run. So this provides components access to permission checking, the localizable resources, and access to resources outside the application, such as the file system, database, and device preferences. Context is also used to start activities, so go from one activity to another, and start services within the application. There are two very important subclasses of context: activity and service. So as we said before, a service, in this case it's the service object, it performs some long-running operation in the background or provides some functionality that isn't user-facing. An activity, though, is a user-facing component, and this is what displays information to the user and allows the user to interact with the application. The intent object represents an intent and describes all of the attributes of a component that can fulfill that intent. When you're issuing an explicit intent, you can set the component name attribute of the intent object to indicate which activity or service should receive that intent. You can reference the component to which the intent is delivered by its name, its class, or if you have an instance of it. For implicit intents, you specify a category of the component that can satisfy the intent. So for instance, the voice category refers to activities that support voice interaction. Or category app music specifies activities that work with music files on the device. There are dozens of built-in categories that describe many of the activities that you might want to invoke with an Android app. In addition to information about the specific activity that should be triggered or a category of activity, the intent also conveys some additional information about the action to be taken with that activity. There's a property called action, which specifies what the activity should do when it receives the intent. There are lots of built-in actions such as view some data that was sent as part of the intent, or send the data to a different application. Depending on what the target activity does, you can also create your own action strings for more custom and specific application interactions. An intent also has a data property, which provides a URI that identifies the data associated with the intent. An intent can also express the type of data, the MIME type of the data that you're looking to either send to the activity or receive back from the activity. You may notice that invoking intents is kind of like invoking a REST API, in that you've got some piece of data that has a location, a URI, that specifies it, and then it also has a data type in the MIME type. You can pass additional information via the intent in a bunch of key value pairs in the extra attribute of it. And finally, an intent has a bunch of flags that provide metadata about the intent, such as whether or not the intent should be launched in a new task. Activities are really important, so I want to dive into some more details about what they are and how you can work with them. So as we said before, an activity represents a single screen that the user interacts with. So much like servlets, Androids don't have main methods. Instead, their activities serve as entry points. And so this is important to note. Android applications have multiple ways of interacting with them, and some applications, depending on their usage. However, each application does have an activity referred to as the main activity, which is the first activity that's started when the application is launched. So when you think about your Android application, it likely consists of multiple activities, multiple screens, multiple services, and can then interact with other applications through their services. So really there are multiple entry points to an Android application. And this is certainly different from a command line utility and even different from a web application, although I suppose a web application can have multiple servlets. The models are kind of similar. So as an example, you might have a chat application that could start a camera activity when the user wants to send a picture. And all of this is accomplished via intents. Activities for your applications should descend from the Android App Activity class. Each of your application's activities should be declared and described inside the Android manifest.xml file for that application. Inside the XML file, each activity is described by its class name. You can specify the icon, which theme it uses, the screen orientation, all sorts of good stuff like that. The manifest also provides what are called intent filters for each activity. Intent filters inform the Android operating system that the activity can be invoked implicitly via an implicit intent. And this is where you specify which actions the activity supports, such as send data or web search. And if your activity responds to implicit intents, you need to have a category of default. The manifest also declares which permissions are required to start an activity. So in order for one activity to call another, the calling activity must have the same permissions as the activity that it is calling. All activities go through a life cycle. It's a multi-phase life cycle, but it's a pretty important concept to understand. As an activity transitions through its life cycle, there are callback methods that all begin with the word on that are invoked. The activity object is responsible to responding to these lifecycle changes and doing things accordingly. Now, some lifecycle transitions are determined by the user or by the application. Going from one screen to another, going back to the home screen, those kinds of things are determined by the user. However, there are other lifecycle transitions that are triggered by the operating system itself. So for instance, as it's looking to free up system resources or perform activities like shutting down the phone, I suppose, it will also interact with the activities, give the activity an opportunity to respond to the change in its lifecycle. It's important that Android applications properly handle lifecycle events to make sure that bad things don't happen. So properly handling lifecycle activities ensures that the app doesn't crash if the user switches to a different app or gets an alert. Also make sure that the user doesn't lose their current state if they switch applications or screen orientations. And also make sure that an activity doesn't consume system resources when it's not in use. So again, an activity can transition through several states over the course of its lifetime. This diagram depicts the states that an activity can go through, and with each state transition, there is that callback method that begins with the name of on that is invoked to allow the activity to respond to that state transition. One thing that's important to note, that even if an activity is not visible, the activity can still exist. It might be in a dormant state or a quiet state and needs to be woken up again before it can interact with the user. And to reiterate, it's important that you understand this life cycle of an activity so that your activities can react to changes in their life cycle and ensure that they are well behaved. The reality of Android application development is that the runtime has a lot of control over the application and over what the application does, and probably more importantly, when it does it. This is essential on a small device that has limited resources. The operating system has to be pretty strict about enforcing things so that applications have an opportunity to run. This means it's incumbent on your application and your activities to respond to these events when the operating system decides that it needs to free up resources. So if an Android activity needs to persist some state, information the user has entered but perhaps hasn't committed all the way back to the system of record, the application can do so by using a bundle object that provides name-value pairs for a number of different data types, byte, character, car sequences, etc. So this allows you to quickly save off application information as an activity transitions through its lifecycle. Now let's talk about some of the callback methods that are invoked on activities over their lifecycle and discuss the kind of things they do. The onCreate method is invoked by the Android runtime when an activity is first instantiated. OnCreate is responsible for initializing the UI state for the activity. One of the important things that it does is that it invokes the setContentView method on the activity that registers the UI objects for that activity. The bundle that's provided to onCreate contains any saved state associated with the activity. If there isn't any saved state, null will be passed to onCreate. Your activity may override the onSavedInstanceState method or the onRestoreInstanceState method to manage the activity's state as it transitions. After onCreate has finished, the activity's onStart method is invoked by the runtime. Alternatively, onStart may also be invoked after a stopped activity has been restarted. OnStart is responsible for performing UI startup activities such as drawing the UI components, the visual elements, starting animations, things like that. Note that the inherited onStart method from the base activity class performs some very important operations. So when you override onStart, it's essential that you must invoke super.onStart. Note that onStart is meant to execute pretty quickly, and as soon as it does, the activity moves into the resume state, meaning that it's up and running. The onResume method is invoked when it enters the resume state, and this is a place where you should initialize any components that were released in the onPause method if you're coming back from being paused. And note that the resume state is sort of the normal visible state of the activity, and it'll remain in this state as the user interacts with it until some event causes it to be paused. So for instance, receiving a phone call or navigating back to the home screen. When the user leaves some activity, the onPause method is invoked. OnPause ought to do things like stopping or slowing down in-progress operations. So if you're communicating with some other service, like the GPS, if you're releasing system resources, connecting to the network, anything that might impact battery life, this is an opportunity where you should stop doing that or at least slow it down because your activity is, well, no longer active. It is expected that activities aren't in the pause state for very long. This might be a quick context switch to go to a different activity, or again, check an IM that just popped up, something like that. Again, the onPause method is only meant to perform a handful of operations. It should not do big, potentially expensive things like save data, make network requests, call the database, stuff like that. That functionality should be done in the onStop method that we'll talk about shortly. However, onPause is a perfectly good place to save in-application state, such as text that's been entered into text fields, anything you want to be restored and want the user to see again when it returns to the visible state after being paused. Activity in the pause state may return to the foreground and onResume will be invoked, or it might become completely invisible and onStopped is invoked. Activity transitions to the stop state when it's no longer visible to the user, and its onStop method is invoked. OnStop is a place to release or significantly adjust system resources that are being used and things that aren't visible to the user. So this is where you would stop your animations, maybe switch from fine-grained location updates to more coarse-grained location updates, etc., etc. And again, it's the place where if you're going to be doing CPU-intensive teardown operations like saving a file to a database or making one last network connection back to a service, OnStop is the place to do this. Note that a stopped activity still resides in memory. The object is still around, is taking up some memory, but it's not attached to the window manager anymore. So the UI resources are no longer available and can be recycled and used for other things. However, the state of the UI still resides in a bundle if you've saved your state off to that. When the activity resumes, you still have whatever state you've saved behind. Towards the end of an activity's lifecycle, it goes into the destroyed state, and before it does so, the onDestroy method is invoked. This is when the activity is finished. The user maybe has dismissed it, or you explicitly invoke the finish function. Activities can also be destroyed when there is a sort of fundamental configuration change, such as a device rotation, that will cause the activity to basically be blown away and then potentially recreated in a different configuration. In this case, the system will create a new instance of the activity. Android does let you distinguish between the move to destroyed, and the move to finish with the isFinishing method to determine if your activity is finished or merely being destroyed. And finally, onDestroy is the activity's last opportunity to release any remaining system resources that it's been using if you haven't already done so on onStop. Now, I had mentioned before that the Android runtime will act to free up resources when it needs it. So as a result, activities that are later in their life cycle, that have been paused or are ready for destruction, are more likely to be destroyed than those that are earlier in their life cycle. Note, though, that the user expects a consistent experience after the activity has been destroyed. So it's important that your activity handle the changes in life cycle to make sure that UI state is not lost just because the device is rotated or they switch to a different app. You want your applications to be well behaved. I just want to reiterate that the activity does maintain some instant state even when it's destroyed. There's a little bit of information about each view object in the UI. These are the UI elements that are in the activity. That information is persisted in a bundle object, which then gets sent to methods like onSavedInstanceState. Once again, bundles are great for small amounts of data, but if you're dealing with large amounts of data, you'll need to have another strategy for saving all of that data. So we've talked about the state transitions that an activity goes through over its lifetime. One of the things that triggers a state transition is the launch of a new activity. One activity wants to launch another activity. And so this is initiated by invoking the startActivity method on an activity, and it's sent an intent object that specifies what activity should be launched. So again, if there's a specific activity that you want to invoke, you make an explicit intent, and you provide something like the new activities class to the intent. And you can also use the putExtra method to pass some data to the new activity through the intent. StartActivity is kind of a fire and forget it method. It goes and launches the new intent, and then the calling activity goes about its merry way and actually usually doesn't do anything else. It'll get paused or put into a different state. If the activity that issues the intent wants to get some other information out of the activity that receives the intent, it can call the startActivityForResult method. What this does is it fires off an intent and associates an integer identifier with the invocation of that activity. The child activity that receives the intent can perform its operation and then invoke the setResult method with an int code that conveys whether or not the activity performed the desired operation associated with the intent. The child activity can pass data back to the parent, the activity that invoked it, via another intent. In terms of state transitions, here's what happens when you have an activity A that transitions to an activity B. So activity A issues off the intent and then enters either the paused or the stopped states. It's up to the Android runtime to determine which state it goes into. In parallel, activity B is created. And then there's a very explicit and deliberate order of operations that occur between the two activities. So the onPause method of activity A is invoked. Then activity B's onCreate method is invoked. Then activity B is started and the onStart callback is invoked. And activity B resumes and the onResume callback is invoked. And now the user focus is on activity B. And then in the case where activity A loses user focus, which is a lot of the time, then activity A will transition to the stop state and the onStop callback will be invoked. Activities are the primary means through which your user interacts with your Android application. Services, on the other hand, represent work that's done in the background of an application and interacted with by other services. And just like activities, services are associated with applications, and unless you say otherwise, a service will be run in the same process as its application. Meaning it'll be run as the same user and be able to communicate easily with activities and other services within that application. You may have the service choose to work in its own thread or as a separate thread to allow your application to do more things at the same time. Now, applications that want to interact with the service perform an operation called binding, which allows that application to access the service remotely, essentially, because it'll be in a different process. However, the bind operation on a service provides you with what appears to be a local Java object whose methods you can invoke directly. So interacting with services is really quite natural, and your code doesn't really need to be aware of the fact that it's invoking a service method as opposed to any old Java method. Now, if you'd rather, you can also invoke with services, treating them more like remote objects that are interacted with via intents. This is a little bit more awkward, but may be appropriate in some situations.